Something unexpected just happened, and it pushed monitoring teams from calm observation into high alert. At first, it looked like a mistake, a stray spike in ultraviolet readings, a blip that engineers blamed on instrument noise. But the numbers didn't vanish, they climbed. Wave after wave of hydroxyl emissions appeared in spectra where no one expected them, the unmistakable fingerprint of water being torn apart by sunlight. Scientists muttered calibration until more telescopes confirmed the same pattern. Then someone said it out loud, "This is not noise." For weeks, astronomers had watched 3I, Atlas, move inward like any distant interstellar visitor, predictable, slow, faint. Comets at nearly 3 astronomical units barely whisper. They don't spew water like a ruptured hydrant. Yet that's the image that circulated through message threads and observatory logs, a broken fire hydrant in space. The phrase stuck because nothing else fit. The footage and spectral traces carried an urgency no one wanted to annotate with drama. Multiple teams reported the outflow as violent, sustained, and far beyond what thermal models predicted at that distance. Observatories that specialize in ultraviolet spectroscopy independently measured the hydroxyl spike. Instruments tuned to different wavelengths corroborated increased gas and dust emission. The redundancy mattered. This was not a single telescope fluke. This was a pattern. And patterns force decisions. NASA didn't send an alarm to the public feed. It didn't need to. Internally, the posture changed. Routine monitoring became active alert. Software flags, engineer calls, retask cameras, all the bureaucratic small things that mean, in practice, pay closer attention. Why? Because the simplest, coldest fact of the data was also the most alarming. Atlas was losing water at rates that shouldn't be possible out here. That reality opens 1,000 technical questions and one blunt, unnerving one. If sunlight can't pull water out this far, what's doing the pushing? NASA did not post a panic. It changed posture. It is a small language, software flags, priority queues, extra eyes on telemetry, but it is the clearest sign that something unusual has moved from curiosity to concern. Teams began cross-checking orbital elements, instrument health logs, timestamps. They replayed raw spectra. Volunteers at smaller observatories called their larger counterparts. Confidence rose with redundancy. Hydroxyl spikes in ultraviolet, matching rises in near-infrared gas bands, simultaneous increases in dust scattering. Multiple teams reported the same story. That redundancy mattered. This was not a single telescope fluke. This was a pattern. Why that matters requires a short physics lesson. At nearly 3 astronomical units, sunlight is weak. Thermal models predict a trickle of sublimation, not a waterfall. Most comets this far out exhale only trace gases. Their icy interiors remain insulated beneath processed crusts. Ultraviolet hydroxyl is the smoking gun for water. When H2O molecules break apart under solar UV, they leave a spectral signature we can measure. The spike we saw wasn't a whisper, it was a shout. The mismatch with theory set off a cascade of questions. Could there be a calibration error? Multiple teams already ruled that out. Could solar activity have created a false positive? Solar monitors were quiet. Could a nearby object's glare bleed into the spectrum? Orbital checks showed none. The simplest explanations collapsed under scrutiny. In the lab and in the field, scientists prefer conservative hypotheses, a known mechanism, a tweak to models, a missing parameter. But data is data, and data force them to widen the aperture of possibility. If sunlight alone can't explain this, something internal to Atlas must be driving it. And that admission, the willingness to consider the nucleus itself as an active, evolving system at this distance, is where the tension sharpens. One researcher summed the mood in a single line: "We thought we had seen everything, then the numbers told us we hadn't," is approximately equal to 40 kilograms every second. The number cuts through polite scientific prose. It is not an estimate padded with qualifiers. It comes from hydroxyl emission strengths, corrected for instrument sensitivity and geometry. To non-experts, 40 kilograms per second sounds abstract. To dynamicists, it is dangerous. That mass loss translates to measurable thrust. It should nudge the object's path in a way we can predict. Ultraviolet spectrographs detect fragments of water after solar UV splits them. The hydroxyl band's intensity scales with production rate. Models convert photons to molecules to kilograms. Multiple facilities ran the conversions independently. The agreement is not perfect, but it is consistent enough to demand attention. Other instruments had already reported carbon-bearing species earlier in the approach, but they could not account for this sudden, water-dominated surge. Here is the wrench. Tens of kilos per second act like a slow rocket. Physics gives thrust, thrust gives acceleration, acceleration should show in the trajectory. Yet when dynamicists ran the numbers, the observed motion did not match the thrust implied by outgassing. Some portions of the path agreed, others deviated in subtle ways that models couldn't reproduce. Simple reconciliations surfaced. Angled jets, rotational averaging, channeling through porous crust, transient vent stabilization. Each tweak eased the gap but left residuals. Teams simulated a range of geometries and rotation states. They introduced secondary gas streams and seasonal effects. The models grew complex, but the mismatch persisted. In a few runs, the predicted wobble was clear and measurable. In reality, the wobble was irregular and shifting, as if the forces themselves were changing with time. This is not evidence of the exotic. It is a stubborn mismatch, a crack in our models, a powerful, water-dominated outflow at an improbable distance, and a trajectory that refuses to behave. That contradiction forces us to ask harder questions about Atlas's inner architecture, hidden reservoirs, and processes we do not yet include in simulations. This is not a local comet. It is a traveler from between the stars, an object older than our Sunday. For billions of years, 3I Atlas drifted through interstellar space, exposed to cosmic rays and slow chemistry that rewrites surfaces molecule by molecule. Those rays strip light elements, darken exposed layers, and build a hardened shell. Estimates place that shell at many meters. Some models suggest 15 to 20 meters far thicker than the mantles formed by ordinary solar weathering. Under that shell, interior ices should be sealed and inert. At nearly 3 astronomical units, sunlight should only nibble at the surface. Deep reservoirs should remain untouched. Solar system comets respond to heat closer in. Interstellar bodies, processed by galactic radiation, should be even more resistant. Atlas's size only compounds the puzzle. It is larger and more massive than the first known interstellar visitor and should, by every measure, be less reactive at this distance. And yet Atlas vents like a body much closer to the Sunday. If cosmic rays hardened the exterior, then what we see now suggests a failure of that armor. A crack or rupture could expose ice unchanged, since the object's formation material that has not been heated by any star for billions of years. The thought is electrifying, a direct glimpse into pre-solar chemistry and a rare chance to sample primordial volatiles. But the failure still asks a question: why now? Why at this point in its orbit? A shallow fissure might produce a brief spurt. A deep breach can create a sustained conduit, feeding a jet for days or longer. The difference changes everything from how much mass the comet can lose to the trajectory disturbances engineers will track. That distinction separates a strange anomaly from a discovery that could rewrite our models of interstellar bodies. Scientists know a single deep exposure could change how we think about the inventory of water in the galaxy. Armor failed. Short sentence, long consequences. Imagine a shell 15 meters thick cracking open. Inside, ice that has never met sunlight sits cold and volatile. The instant that skin breaks, heat, even the thin warmth of distant sunlight, begins to penetrate freshly exposed layers. Vapor forms, pressure climbs, and with nowhere to bleed off that energy, the trapped gas finds the weakest outlet. The result is not a gentle puff. Laboratory studies and analog experiments show outgassing can spike from near zero to explosive in moments once a fresh surface is exposed. The fracturing hypothesis is blunt and physical. A brittle crust, undermined by microfractures or internal stresses, snaps. A localized rupture becomes a conduit, and the conduit becomes a jet. The jet's composition matters. If the crack reaches deep, untouched ice, the outflow will be water-rich, precisely the signature we observed. If it just grazes processed layers, then carbon-bearing molecules dominate. The water dominance we measured points to exposure of genuinely pristine material. There are cinematic images that flow from that possibility. A time capsule pried open, a column of ancient ice and dust streaming into sunlight for the first time in eons. It's evocative, yes, but it also fits the physics in a way other hypotheses do not. It explains rapid onset, high production rates, and the sustained nature of the plume at least qualitatively. And yet, it opens another problem. A jet that vents tens of kilograms per second imparts thrust. That thrust should alter the comet's motion in predictable ways. In many simulations, a ruptured conduit produces a measurable acceleration and a characteristic wobble. In Atlas's case, the motion is messy and partially mismatched to the thrust we estimate. The fracture model explains much, but not everything. Outgassing is thrust. It should shove the comet. That principle is simple. Mass ejection produces momentum change. With roughly 40 kilograms per second leaving Atlas, dynamicists expected a clear acceleration, a measurable nudge, a wobble, a calculable drift. Instead, the motion refuses neat description. Modelers tried the usual fixes. Tilt the jet, let rotation smear the impulse, simulate porous conduits and multiple vents. Each tweak moved predictions but never closed the gap. Some runs produced a clear wobble, others matched fragments of the track. Residuals remained small, stubborn, growing as new data arrived. Why the mismatch matters is not academic. If thrust vectors don't sum to observed motion, then either the internal geometry is stranger than we imagine, or additional forces are at work. Could electrostatic lofting, magnetic interactions, or asymmetric dust shedding create unexpected torques? These are conservative extensions of physics, testable if we can see them and measure their signatures. The jet is oddly stable, yet the acceleration signature is irregular, as if the drive itself shifts faster than our measurement cadence. That suggests transient internal dynamics, channels widening or plugging, rotating vents that swap thrust vectors, or grain avalanches that change mass flow. Each hypothesis requires internal structures we cannot yet confirm. And then the blackout. Atlas slips behind the sun from Earth's view. For days, our ultraviolet and optical eyes are blinded. Simulations must carry that uncertainty. Mission planners cue every capable instrument for the reappearance. Dynamicists watch plots with furrowed brows, mission designers assess navigation margins, observatory teams prepare coordinated campaigns. Everyone knows that when the object returns to view, the first frames and spectra will be decisive. Some researchers already compare this to earlier perihelion anomalies, patterns that forced model revisions, and they admit this could be another such inflection point. We are blind for now. It reads like a short sentence in a long argument. The object slips behind the sun, and with it slips our certainty. But the blackout is not an ending, it is a hinge. When Atlas emerges, it will hand scientists clear tests. Behaviors that confirm a crustal breach, or behaviors that force a deeper rethink. First, the coma. If the fracture was shallow and temporary, hydroxyl will fade and dust production will settle. If the breach is deep, the coma will grow brighter, bluer, and richer in pristine ice grains, a chemical fingerprint from before the sun existed. Second, color and brightness curves will reveal grain sizes and ejection velocities. Third, detailed trajectory tracking will finally tell whether the jet's thrust integrated cleanly or left an irreconcilable trace. Each outcome sketches a different future. A fading plume closes the file on a dramatic but understandable event. A strengthening, water-rich outflow promises a direct look at pre-solar chemistry and may rewrite inventories of galactic volatiles. A persistent mismatch between thrust and motion would force the community to expand models to accept new internal architectures, or new processes, or both. The stakes are not just academic. Understanding interstellar bodies touches on where water and organics travel in the galaxy and what building blocks migrating between star systems bring with them. For engineers and mission designers, the dynamics define rescue windows and navigation strategies. For curious minds, this is a rare live experiment in cosmic archaeology. We will watch the first footage together. That first video, the one captured by China's deep space camera and shared with the world, will be the evidence everyone parses frame by frame. It will be compared, measured, and debated. It will either comfort us with familiar physics or push us to expand them. Until then, we wait with a scientist's mixture of impatience and awe. The universe is testing a model. and the result will change our understanding of objects that arrive from between the stars.